Hello, and welcome to this presentation, which gives an overview of optical loss testing practices and equipment for both single-mode and multi-mode fibre optic systems. Fibre optic loss or attenuation testing measures optical transmission efficiency and is used for acceptance testing of components and systems. It is comparable to measuring RF signal loss in a coaxial copper link and even shares a similar measurement unit, the decibel. Loss testing is important for three reasons: to ensure that systems perform as expected, to compile acceptance test reports, and to act as a reference for maintenance operations. So correct testing is an important business issue. Generally, the business value greatly exceeds the testing cost, which in itself is a significant factor. Inadequate testing typically affects both profit and business reputation, and can result in liability costs due to a lack of due diligence. In practice, the major testing cost is usually labour. However, personnel often have limited training or experience, particularly when responding to a critical failure. In any case, management must trust that the operator has done a good job. So it is important that equipment and procedures are accurate, reliable and easy for the operator to use in all expected situations. Here in Australia, for example, our customers operate in tropical damp heat, extreme dry heat, extreme dust, and in remote locations. Optical loss testing is performed at all phases from R&D through to manufacturing, system installation, and maintenance. So there are many different requirements for test accuracy, speed, and flexibility. There are various general management issues to consider. Users must be trained. At the worksite, users need adequate time and authority. A test equipment assurance program is needed. Test leads and through connects require a program of inspection and replacement, since they get damaged or worn. Test results need careful management, which is time-consuming. Optical cable loss is wavelength dependent, so testing is performed at current and expected operating wavelengths, such as 850 nanometers, 1310 nanometers and 1550 nanometers. Testing may also be performed at long wavelengths, such as 1550 nanometers or 1625 nanometers, to help identify cable installation faults. We will now show a few features of Kingfisher KI7000 and KI3000 series instruments. The instrument is comfortable to hold for extended periods, for either left or right-handed personnel. The backlit LCD provides high contrast, and there are operating instructions on the rear label. We will move to the battery compartment. Batteries have a life of 190 to 1,200 hours, so under heavy use they are changed every few months. This avoids rechargeable batteries and saves labour. If rechargeable batteries are used, they are removed for charging. The external power supply runs the instrument but does not charge the batteries. A battery size converter may also be supplied, so either AA or C size batteries can be used. The instruments turn off automatically to save power. Alternatively, if the power button is held down during turn on, the instrument will stay on. A hidden keypad for advanced features keeps the main keypad simple, which makes operation easier. Our patented optical connector offers numerous practical benefits. The same arrangement is used on both test ports of the instrument. When adding a patch lead, rotate the connector to the open position for easy access. Insert the test lead and then close both the connector and the protective boot. Connector adapters are easily removed using one of two methods. Either way, it is usually easier to grasp the adapter with the test lead in place. On older instruments, the connector is rotated to a halfway or mid position, and then the adapter can be pulled off. On newer instruments, a button on the rear of the instrument is depressed and the adapter is pulled off. To replace the adapter, rotate the alignment slot the correct way and then push it in. 3 common connector styles are supplied: SC, ST and FC. Other styles available include the small form factor, LC and MU connectors. These connectors all use a high quality ceramic sleeve, which gives a long and accurate service life. It also avoids metal dust contamination of installed systems, which can cause failures in high-powered fibre systems. The connector adapters are inexpensive, so regular replacement is practical. It is easy to inspect and clean the connector assembly or change a failed through adapter. Auto-test is an important feature that allows test equipment to communicate across a system being tested using only one fibre. Light sources transmit data, power meters receive auto-test data, and two-way testers communicate in both directions. Auto-test is compatible across our range of instruments. For example, power meters receive data from two-way testers, and light sources can send data to a two-way tester. And here Brian is showing you a light source operating with a two-way tester. This provides operational benefits, since different staff may have different equipment, but need to work together in field operations. Auto-test instruments display in real time. Since all loss testing can be performed using auto-test, this greatly reduces skill level and improves productivity. Here is auto-test in operation using a 2-wavelength source and power meter. The meter shows the 2 source wavelengths. A button push displays the results for just 1 wavelength. The absolute power display shows the approximate source power level using data transmitted from the source. The relative display shows the reference level stored on the power meter. Here we see auto-test on a two-way tester. The display shows the real-time average loss measured in both directions on one fibre and is identical on both instruments. The display can also show just 1 wavelength. The real-time display saves substantial effort and allows staff to correct test errors in real time. Two-way instruments can also show a pass-fail indication. Now we will show you KIT's reporting software, an out-of-the-box solution for many applications. KIT's is Windows XP compliant and interactively controls the instrument. So there is little need to use the instrument buttons when it's connected. KIT's is an extension of Microsoft Excel and has a comprehensive online user manual, all of which minimize user training. KIT's has 4 main worksheets. First, a real-time display, which is useful for training and diagnostics. It also shows real-time data being received. For example, here is data being received from a two-way tester. Data logging is useful for finding intermittent faults and doing long-term testing. Label printing with flexible label formats and an unformatted instrument memory dump. Loss testing, which we will examine in more detail. Using traditional methods, the creation of customer reports accounts for half of the overall testing cost, and the data manipulation causes errors. We will now show you how KITS either eliminates or reduces both of these. There are three general ways to use KITS for loss testing. A notebook computer can be connected to an instrument and live data inserted directly into a custom report. This is best suited to high fibre counts and offers the highest productivity. Alternatively, data can be stored in instrument memory and downloaded into the report later. This is best suited to sites where there are few measurements at any one location. And lastly, data can be entered into the test report manually if using legacy or low-end instruments such as a KI 3600 power meter. Both customer acceptance reports and dialog boxes in KITS can be customized by the user for any language or terminology. Extra columns can be added in Excel to show other information, and data can be password protected. We will now show a user setting up loss testing. First, work site details are entered, and the number of fibres. This sets the spreadsheet to the correct size. Next, detailed test parameters and wavelengths are set. Pass-fail parameters are defined. Custom or industry standard values can be entered. There is sufficient flexibility to allow most work practices to be used. The fibre numbering can be changed as required. And the user can click on an active cell to insert measurement data. We will now discuss connectors and test leads. Test lead fibre type and connector type should both match the system under test. Practical testing is performed with a low-loss test lead attached to the instrument for the duration of the test. These leads form part of the test apparatus. Ceramic connectors have a lifetime of about 1,000 insertions due to mechanical wear. So in a test environment, test leads and through connectors require a management program so that they are regularly replaced. In use, connector ends must be regularly inspected with a good quality microscope. So each test operator needs a microscope. Here is an example of an inexpensive microscope suitable for this sort of work, available with either ×200 or ×400 magnification. During testing, connector ends are cleaned before each insertion. This is time-consuming but important. So each test operator needs cleaning materials. Here we are using a simple cleaning device. We will now explain the difference between single-mode and multi-mode testing. Both types of fibre are now often found at one site. Traditional assumptions about associated technical skill, data rates and economic value of the link are now false. There are now many high-value, high-speed multi-mode links, and many low-value, low-speed single-mode links. Single-mode testing is more accurate and repeatable. It uses equipment fitted with laser sources at typically 1310 nanometers and 1550 nanometers, and power meters using indium gallium arsenide detectors or germanium detectors. Multimode testing is generally less accurate and repeatable. It uses lead sources at typically 850 nanometers and 1300 nanometers, and power meters using either germanium detectors or silicon detectors. Indium gallium arsenide detectors do work, but are very inaccurate at 850 nanometers. More advanced DWDM or CWDM systems use other wavelengths from 1270 nanometers to 1610 nanometers, and may be of either fiber type. Multimode test results can be very variable. However, this can be greatly improved if three conditions are met, which are embodied in recent standards. First, an LED source is used. This avoids unstable measurements caused by modal interference from laser sources. Second, the LED source is selected to ensure that the light fills the entire fiber core. This is termed a Class 1 coupled power ratio. Third, a mandrel wrap is used on the source patch lead to remove unstable modes from the outer edge of the fiber core. This does mean that the measured loss may not be the same as that seen by an operational system. However, this compromise is required to achieve measurement repeatability. This brings us to the end of this presentation. Thank you for watching. We hope you found it useful. This video can be followed by a second presentation, which shows some detailed test methods.
Thank you for watching our presentation. We trust you found this valuable.